Let us consider non-uniform magnetization. So here, whatever the internal currents generated by these tiny loops, right, we consider same size chunk, but the current generated by this particular same size chunk could be different, right? So that is why if the current bound current is different, you can see this particular diagram. Okay, so there are two chunks of the same size is there, right? The bound current generated by the left hand side small tiny chunk, it is smaller in size compared with the one which is on the right hand side. So you can see this. So you can see this is shown by the width of that particular green band, right? Okay, so it is a small ix, right? Whereas on the right hand side chunk of the same size, if the magnetization is non-uniform, that means it changes from the position to position. So here we consider the first chunk position at y and the second chunk position at y plus dy. Okay, they are pretty close. So the magnetization is uniform. So along the z-axis, we are checking magnetization divided by this chunk. So here it is m subscript z at position y, then n subscript z at position y plus dy. So these two chunks are presenting different magnetization, though they are of the same size. So it is a case of non-uniform magnetization. Okay, so here the bound currents are different in their magnitudes. That is where the different magnetization creeps in. Okay, so we consider the chunk which is on the right hand side at y plus dy carries more bound current. That is why more magnetization present at that particular position. Okay, so the z coordinate of both of this chunk is same, right? That is a z over here, right? Whereas y coordinates are different. Whereas y coordinates are different, right? So when we consider this facing side, right? Okay, we are not worried about the facing side because that is on the boundary. So right now we consider this particular side, right? Okay, so I'm marking this particular side. So this is the side which is along the x-axis, which is along the x-axis, and our positive x-axis is shown by this arrow. You can check this, the positive x-axis direction. So this particular side we are worried because along this side these two chunks are in contact with each other or very close to each other, very close to each other. So here the direction of the current is along this direction. When we consider this particular chunk, the direction of the current is this. The direction of the current is this, and this capital Ix for the right hand side chunk is larger than that on the left hand side. So definitely, right, when we consider the net current, right, net current, when we consider it is right along the positive x-axis direction, along the positive x-axis direction. So here we are writing this net current in terms of, right, difference of m and multiply by dz. Now this is from the expression I is equal to mt. You can see that I could be written in terms of magnetization and the width. Okay, so which width we are considering? We are considering dz, right? That is corresponding to t. You could see that that is corresponding to t. Okay, so you can look at the earlier diagram. So here this t corresponds to dz, that's the dimension of the chunk along the z-axis direction. So right now we are looking right along the z-axis, right? What is the difference in the magnetization? So there are three axes are there: x-axis, y-axis, z-axis. We are looking along the z-axis. What is the difference in the magnetization? Okay, so when we work it out, right? So we are writing Ix in terms of the difference in mz at two positions, right? Because that is why the current, this particular difference in current, right, which gives us this difference in magnetization. So that could be simply written as change in the mz over change in the y multiplied by dy. So it is right. Normally we are doing the right measurement along. Let us suppose say we are going for this y-axis and x-axis. So we are making use of the slope, right? Okay, so let us suppose say this is the direction and we want to, okay, let me put it y here and x here. Okay, so in that case, right, so along this, if I want, right, what is the dy, the change in the this, so I'm going for the slope multiplied by dy. So same way we are doing it here, right? Okay, so dy comes here, that is the appreciable change, right? We what is the actual change along the y-axis? So we are going for the slope, right? That's the change in the m, right, with respect to change in the y, and then we multiply by thickness dz. Okay, so when I take this thickness, right, on the left hand side, I'm getting, right, okay, a kb. But when I go for the dy dz, right, so that is the area. I'm looking at the area. I'm getting jb. That's the volume current density. So why do we need volume current density? Because we are inside the magnetic specimen. We are not looking at the surface like we saw earlier. Okay, so all these chunks are arranged inside, and we want to get, right, what is the difference in the current, bound current inside, and that refers to the volume. So that is why we have to take into account, right, JB. That is a volume bound current density. So it is Ix over dy by dz. Please note it carefully, right, where the dy comes, where the dz comes, right? So which area we are looking into? So we are looking into this area. Check it out here. Dy by dz. We are looking into this area, right? Okay. And this area, right, is taken for the calculation. So JBX is there. Now X, because the current is flowing along the x-axis direction inside the volume of the specimen. So that we are getting in terms of change in mz with respect to change in y direction, right? So how the mz changes when we go along the y-axis direction. Okay, so that change in mz with respect to change in y gives us jbx. That's the volume bound current density along x-axis.